people. Okay. Hello, everybody. I'm sorry for the small delay in the presentation. We were solving some technical issues, but now it's a pleasure to welcome you all for the seminar series of the RGIK group, the Rock Glacier and Inventories in Kinematics. And today it's a pleasure for me to introduce Eliseo Flores from Universidad Nacional de Córdoba, if I'm right, CONICET, working on the inventory and kinematic of rock glacier in James Ross Island in Antarctic Peninsula. And I think we have 15 to 20 minutes. It's very easy going, the presentation, and then we have some time for discussions or questions to Eliseo after the presentation for 5 to 10 minutes, either on the chat or raise your hand. So thank you again for accepting the invitation, Eliseo. The floor is yours for the seminar.
Okay, Sebastian, thank you. Good morning, everyone. Good morning, at least here in Argentina. I'm actually working in my PhD. This is part of my PhD. I'm studying rock glaciers, doing inventory and measuring the kinematics in different parts of the Andes, in northwestern Argentina, in Tierra del Fuego, and also in Antarctic Peninsula. So this is part of my PhD. These are preliminary results. I also work with Matteo Martini and Jorge Strelin. They are my advisors. The site of work is James Ross Island in the northern part of the Antarctic Peninsula. Most of the island is completely covered by glaciers, except by the northwestern part, which is one of the biggest areas in the northern peninsula, in the Antarctic Peninsula, without glaciers. This is consequence of western winds that cross the Antarctic Peninsula. When they cross the peninsula, they become drier and warmer. So this part of the island don't present glaciers. The mean annual temperature is 6.6 negative degrees. And the precipitation from this precipitation data is from the World Glacier Monitoring Service, from Bahía del Diablo Glacier here in Vega Island. It varies a lot, temporal and spatial. The precipitation close to the sea level is lower, it's between 170 and 200. In higher elevations, it reaches 600 millimeters water equivalent. So some previous works and the motivation for doing this inventory in this part of the Antarctic Peninsula is that there have been many works there. Some of them, they include the whole island, but they have a very low resolution. And more modern works, they only work in the northern part of Ulu Peninsula. And also the main problem is that different authors classify the same landform as different, with a different name. For example, here, all these pink landforms are classified as rock glaciers, and this landform is classified as a moraine. While in this other work, all of these landforms are moraines, ice-core moraines. And this is an older work, which one of the landforms is a rock glacier, that here and here are moraines, and some landforms that here are moraines and here are rock glaciers, here are mapped like a landslide. So the main idea of doing a new inventory here, it was to include the whole island and also to apply some of the guidelines of the IPA action group to differentiate the different landforms from the rock glaciers. The methodology, the satellite image from Chambers Island are usually very bad quality because they have clouds or they have a very low resolution. So I have to process aerial photographs that were taken many years ago with digital cameras. I use Metashape software to produce digital surface models and photomosaics to do the mapping of the rock glaciers. I try to apply some of the IPA Action Group guidelines and also some of the work of Janky 2017. In this work, he applies some classification to distinguish between debris-covered glaciers and rock glaciers from satellite imagery. And then we choose some of those rock glaciers for monitoring, for measure the surface displacement using differential GPS measurements. The result of the inventory was 72 rock glaciers. Most of them are located in the northwestern part of Chambers Island, and some on the southeast part, which are the areas that don't have glaciers. And we include also some landforms in Vega Island. One time that after we have the inventory, I extract some morphometric parameters, basics. The elevation of the rock glaciers, they develop between the sea level 400 meters. They don't develop at higher elevation because the island it's covered by ice. I also include, because I compare with other sites of the Andes, which are the main lithologies of these rock glaciers. As Chambers Island is a volcanic island, most of the rock glaciers are compounded by volcanic rocks, and only some of them include sedimentary rocks from the bedrock of below the volcanic rocks. And we also extract the aspect of each rock glacier. In other sectors or areas in the Andes, there is usually a strong control of solar radiation. The rock glaciers are in south face, but here in Chambers Island, they don't show a preferential distribution regarding the solar radiation. They have the distribution more to the west and to the east components. We think that this is controlled mainly by the topography of the island and not by the solar radiation. And as I include some criteria from the guidelines of IPA, I include the spatial connection of the rock glacier in the attribute table. Most of the rock glaciers here are talus connected. Like this example here, they form at the foot of these cliffs. These are volcanic cliffs. They are very common in the geomorphology of the island. Then they are followed by glacier connected glaciers. Like here we have the glacier, then debris covered area, and finally the rock glacier. And we have only a few debris mantle and glacier force field connected, like this example here, where the rock glacier forms from a little ice age moraine, or debris mantle slope connected, where this slope is there isn't a marked head wall here that provides sediment. From those glaciers, we choose 4 rock glaciers for GPS measurements. One here, this is called Ring Rock Glacier at the foot of Ring Cracks. And 3 rock glaciers here in this area called Tumbledown Cracks They are also developed at the bottom of these cliffs. This is a ring rock glacier. Here you can see the cliffs of ring cracks. Below the rock glacier, it's the coast. This rock glacier, we did first a detailed mapping after doing a photogrammetric flight. It presents a good development of ridges and furrows, but it also presents some scarps and cracks that we interpreted as a process of destabilization. There are also some scarps here, but they are it's not easy to distinguish them from the ridges. And in this rock glacier, we mark 16 boulders for measuring the displacement. We were able to visit this location in February 2018-19. We couldn't visit during the pandemic, and then again in 2022 and February 2023. So each year we measure the displacement of the position of each boulder. If we consider the 5 years, the average displacement for those years was 12.6 centimeters per year. Here I only consider the horizontal displacement of the boulders, because in the vertical component, the GPS measurements have a big error. So we can establish if the movement of the boulder is part of the movement downslope or it's the measurement of the GPS. Here we can see that the first period between February 2018 and 2019, the movement was around 10.4 centimeters per year. The second period, that includes 3 years, the average annual displacement was 12, a bit higher. And finally, in the last year, 2022-23, it was 1 centimeter more higher. This is other rock glacier that we choose for monitoring. This is located in the southern part of James Ross, of Ulu Peninsula, sorry. Here we mark 15 boulders, and we also did a mapping of the surface of the rock glacier. Here we also map some cracks, features that we also think that are part of the destabilization process. And also ridges and furrows. And this rock glacier also presents some lakes on the surface. The ring rock glacier and this one, they are also talus connected rock glaciers. Here we couldn't visit so many times this location. We could measure the rock glacier in February 2018, February 2020, and February 2022. This rock glacier has a much lower displacement. The average annual horizontal is 5 centimeters per year and varies between 3.1 and 7.3 centimeters per year. Here in the lower part, there are the lower displacement, and here in the middle part, which is the steeper part, we have the higher values. And then we have 2 more rock glaciers, also in the tumble down area. These are much smaller. They have only 100 or 200 meters long width. This is also talus connected. This one was classified as a glacier connected. And both of them show a very low displacement, much lower than the other 2, only a couple of centimeters per year. And then in the second period, from February 2020 to February 2022, they increase their displacement to, in this case, to 4 centimeters, and in this case, only 1 millimeter more. But that's almost in the uncertainty of the GPS measurement. Some discussion about these measurements. All of them in the beginning, the first year or the first period of 2 years, they have lower values, and they increase in this case in two different periods, and in these two cases in the next period. And when we take a look to the air temperatures, this is temperatures from Tumbledown Station, which is the last rock glaciers that I showed. And taking into account the mean annual air temperature or the summer air temperatures, because winter temperatures are always below zero. From March to October, the temperatures are always below zero. So I took the summer air temperatures. We can see an important increase between 2018 and 2021, and it correlates with the increase in the displacement that we are having in the surface of the rock glaciers. That's all. It was very short, I think.
Thank you. Thank you very much for the nice presentation and bringing to us this unknown location of rock glaciers in the Antarctic Peninsula. So I think, yeah, it's a nice job that you're doing. I think the field work there must be amazing. All the logistics involved, and just go there it should be quite complicated, no?
Yes, yes, it is. It's hard to choose the rock glaciers because it's not possible always to visit the same places. So it's hard to keep track of the movement. The idea was to measure each year the same rock glaciers, but it's not possible to go to the same place each year due to the logistic.
Mm-hmm. Nice. So now, do we have any questions from the public? We have a question from Joe. You can say it, or Joe?
No, hi Joe. No, we haven't published the data yet. I think that probably during this year or the next year we will have a publication about these measurements of the rock glaciers.
Okay, so for those who didn't know, the question was if the data was published already. Any other question? Christoph?
Yeah, hi. Thanks for your presentation. Just a question regarding how far the site, the island is. Wouldn't you plan to, or have the idea to use INSAR data to get an overview of the surface kinematics of all the rock glaciers that you inventoried?
I tried to do some INSAR interferograms. I only try using only pairs. I didn't use anything complex like SBS or persistent scatter, only pairs of interferometric image. I detect some displacement mainly in the debris-covered glaciers that move faster, but I couldn't have any good results for the rock glaciers. I think that the problem is the snow cover, the clouds. Perhaps using a more complex processing for INSAR, you can see some movement in the rock glaciers.
Okay, thank you.
Thanks.
Do we have any other question from the public? Either raise your hand or write it on the chat. No, any other question? I might just have a question related to the one that Christoph did, but instead of, I see you did some aerial photogrammetry as well. We saw a very high resolution hill shade from one of the rock glaciers.
Yes.
Are you repeating those measurements? I'm planning to apply some feature tracking or something like that.
It was the idea, but it's all the photogrammetric flights that I did, it was using manual flight. So I'm not sure if it's possible to do some tracking if you don't have the same resolution in each DEM. It was the idea maybe to try to do it. I have flights from each year, but I don't know if you have DEMs from different resolution, if it is possible to compare them to do the tracking. I will try, but I'm not sure if it's going to work.
I think it's possible. You need to kind of homogenize probably the resolution of the datasets and then try to track them once they are co-registered in any case. And yeah, I think it's totally possible.
Yeah, and also I will try to use the same boulders that I measured, like ground control points. The problem is to check in the image, in each photograph, if you can see the boulder and the position of the measurement.
Yeah.
Small point.
Did you use a drone, UAV?
Yes, but Phantom 3 without RGIK positioning.
RTK.
So I have to use many ground control points to have the precision that I need to measure very low displacements.
Okay. Any other question for Eliseo? Comments, suggestions? Not really. So I think we can, many thanks. We have something from Daniel. Good to know. Yeah. Daniel says that you can unmute yourself, or I can read your. Daniel Falaki says, many thanks for the presentation, Eliseo. Good to see more people from Argentina working on rock glaciers. Yeah, we know there are many there.
Thank you, Daniel.
Yeah. Great. Okay, I want to thank you all for attending the seminar today and saying thanks to Eliseo for giving us the presentation, and just remind you that the next seminar will be in the 24th of April, and it will be a special seminar given by the Rock Glacier Inventories and Kinematics Executive Committee on the transition to an IPA standing committee. So everybody is welcome to join that informative seminar about the current plan to be more an IPA action group of becoming a standing committee with a new directive and things like that. So everybody's welcome to attend the next seminar. And thank you again, Eliseo, for giving us the talk.
Thanks to you for the invitation.
You're welcome.